is hard to describe.
Yeah.
Because it incorporates a lot of different aspects of chemistry. So, you get to describe to me all the things that incorporate or define supramolecular chemistry.
Right. So, supramolecular chemistry, in a nutshell, is about...
Hang on, you can't walk away.
So it's kind of about the interactions between molecules. So interactions, kind of intermolecular interactions. Interactions that aren't actually the bonding of an atom to an atom directly. It's about other interactions. Mostly it's about how things pack together, how things arrange with each other. Well, really we're in the inorganic chemistry department here. So a lot of what we're dealing with is metals and metal ions. And we're trying to look at metal ions as components for building out networks and coordination polymers. So, that is empty bottle. Okay, fine, I should have filled up my water bottles. We're using coordination, which is the association between an organic ligand and a metal center. And then we're using that to build out a polymer by having each metal center associated with more than two ligands, and each ligand bridging between metal centers. And by doing that, you generate something that's got 2 or 3 dimensions.
So you have like these like organic ligands in one that. You have like a metal and a ligand and a metal and a ligand. Like
yeah. Difference between this and a conventional polymer is that this is a crystalline. Polymers are usually amorphous, so something like glass. So it's whether they actually have that order between everything, or whether they just have this jump, like a ball pit. Yeah?
Yeah.
Okay. You can kind of see how the balls, they pack close together, but they don't really have any structure. Yep. Thinking of that versus something like a stack of oranges at a fruit shop, where you have each of those layers, where you have that direct, the direct structure to them. So
crystal has that order.
A crystal has the
but
order.
an amorphous solid.
So it's solid and it's connected together, but there's no long range ordering between each of the components. It's essentially like, which is the technical term. You didn't want the technical term, did you? It's not empty enough, okay? There's still some in there. We do a lot of synthetic work. So a lot of what we do is making our own ligands, so that involves a lot of organic chemistry. We essentially take all of these things and then we just let them evaporate. And usually once you evaporate it down, if you assign your ligands and everything right, you've got the right counter ions in there, you've got the right concentrations of everything, then the final thing you get is a really nice single crystal.
Yep.
And then finally, once we've actually made the final solid product, we take down to a diffractometer, which you've got on site. You use it to generate a crystal structure, which is essentially like looking at the things at an atomic scale. So you can see where the atoms are placed inside a thing called a unit cell, which is the repeating unit of the crystal.
Alright.
Yeah.
Show me around. Ooh, oh, is this it?
No, that's the old one. Really use this one.
Ah, okay. Alright, show me the one you do use.
Okay, that's this one over here. You see where it says MOVA?
Yep.
Yeah, that's the tube. So the X-rays are made kind of behind that, kind of underneath that red light that's on at the moment.
Okay.
Atlas is your detector. The X-rays shoot along that little tube and hit this the crystal.
You can see, what is that, like gas or steam or something coming off it?
That's liquid nitrogen, but gaseous nitrogen.
Yeah.
You use a thing called a cryostream, which chills. A little needle goes up to a little pin-sized crystal. So you can see that's what the crystal looks like. It's a little pin that's got a loop attached to the end of it. So there's your pin. You probably can't see the loop on there.
Hang on. There's a pin, yeah.
That's the pin. The pin's about that big on the thing. That's that.
How do you get that on there with such, like, that would...
Do it under a microscope.
How long will it take to do this?
Usually takes, I don't know, it really depends. So on a molybdenum source with a well-diffracted sample, you can usually get a crystal structure within, 45 minutes-ish. This is the pattern you get generating out. And that's essentially a picture taken by the X-ray detector.
You do this for every compound you make?
We either use this or we use the X-ray source out of the signature, which is significantly more powerful. So you can kind of see them. Each of the balls is an atom, and these are part of a repeating structure. The metal center here is cerium, and that's coordinated by 10 oxygen molecules. 6 of which are coordinated, part of your coordinated ligand, and the other 4 are just water. That's also coordinated to metal.
Oh, okay.
So if you're just looking at one layer, just look at one layer there, you can see it's bonded to 3, and that metal center is bonded to 3. If you continue bridging it out, now it's just a mass of atoms, but we can take one of those, and we can just have a look at only the things that it's bonded to, which is just going to be the one sheet. Okay, you can have a look at it.
Oh, cool. So that's just a single layer.
That's just
atoms.
one layer of atoms.
And then you have another layer that looks basically exactly the same as that piled on top of it.
Yep. The crystal structure is really the first thing that you need.
And then you
get a solid, you say, I've got this, what am I going to do with it?
Okay. And then you look at potential applications.
Yeah, pretty much. With the product in it, and the product is the only thing that's precipitated out. Yeah, I probably should, chuck this in the microwave for a second. They always explode every time I put it in the microwave. Has this never happened to you?